Good morning, one and all present here. I, Hiya Gurbani, welcome you all to today's wonderful session on text classification and sentiment analysis. Text classification involves categorizing text into predefined classes or categories based on its content, often utilizing machine learning algorithms like naive Bayes or deep learning models. Also, sentiment analysis is a subfield of NLP, natural language processing, that aims to determine the sentiment expressed in a piece of text, whether it's positive, negative, or neutral. Before we kickstart the session, I'd like to take the opportunity to introduce our director and principal of PIET, Dr. Dinesh Goyal. Under his leadership, the institute has become the first institution to offer engineering education in regional language under the new education policy. Acquiring experience of more than 21 years of teaching, he perceives a keen interest in cloud security, image processing, data analytics, and information security. With the mission to append more and better skill set, he has organized many conferences, workshops, seminars, and FDPs as convener and co-conveners within the short career span. With his great exposure to outcome-based education in higher education, he has been instrumental in obtaining the accreditations for institutions from various agencies like NAC and MBA. He has also been impaneled ambassador in NAC since 2021. With this brief introduction, I would like to invite Sir to enlighten us with his words of wisdom. Over to you, sir.
Good morning, everyone. Am I audible?
Yes, sir, you are audible.
Yes.
Good morning, Mr. Mario Graff. Thank you for joining us. And thank you, IEEE Students Chapter at PIET. So, be a participant. PIET has been a young institute. We are just 17 years old. And in this short journey, we have lived a lot of phases of technical education. And for last 4 years, we have been trying to hand over the baton to students to govern the institution more than us. So we started with student council, where students conduct a lot of non-technical activities. And now for last 1.5 years, we started working on technical chapters so that students can own and govern technical activities also. So we have now IEEE chapter, ACM chapter, and IST chapter as on date, and we are in process of expanding further in the coming years to have more technical chapters. So these technical chapters or the societies of different agencies, forums like IEEE, are great asset to the youth and the professionals who are trying to learn new technology across geographies, across disciplines, or even go to interdisciplinary nature. And I'm quite glad to share that these chapters are quite working well. In last 4 months only, they have conducted 5 to 6 activities each. So today also it's a new edition where Mr. Mario has given his valuable time to come and speak to our students and students of our nearby institutes also, so that how sentiment analysis can be done and what are the different parts of technicalities into it. He'll be talking to you. And sir, I'm ensuring you that the participants will be great learners, and with your session, they'll be trying to have new dimension or new perspective towards their education. With these words, I welcome all of you and thank you everybody for inviting me. Thank you, sir.
Thank you very much for the.
Thank you.
Thank you very much for the invitation. Please interrupt me if I'm not, if you don't understand what I'm saying. As you can see, I'm not a native speaker, so if my English is not is different somehow, just say just please stop me, and I will try to do my best to say it in another way. Should I start?
Yes, please.
Okay.
Yeah, so, you should introduce Mr. Mario first before the session.
Okay.
Yes, sir. I'd like to give a brief introduction about our resource person first.
Sure.
Go ahead. Yes.
Now, to begin with the session, I would also like to introduce Ms. Budesh Kanwar ma'am, our esteemed IEEE advisor and head of AIDS department of PIT, with a dynamic track record of organizing successful events and participating in numerous conferences and workshops. Her contributions have been invaluable. We extend our sincere gratitude for her enlightening insights and gracious presence. Now, to begin with the session, I'd like to welcome our resource person, Mr. Mario Graff. He's a researcher of National Council of Science and Technology of Mexico Communication Infotech. During his sabbatical leave 2021-2022, he was a visiting assistant professor at Colgate University. From 2011 to 2014, Dr. Graff was an assistant professor at the Faculty of Electrical Engineering at the University of Mexico. His research interests are in machine learning, evolutionary computation, and NLP. The research applies EC, mainly generative programming, to supervised learning problems. In this research avenue, special attention has been put on using GP to solve text classification and sentiment analysis problems. And in NLP, the interest is in developing multilingual text representations, which also focus on the representation that facilitate knowledge transfer between languages. We are honored to have you here with us, sir. Thank you so much.
Thank you very much for the introduction. Thanks for the invitation, and let me start about this topic. Today I'm going to talk about sentiment analysis. I'm Mario Graff. Please call me Mario. My first name, I'm good. And everything is online, so you can check it later, or you can check it right now, as you prefer. So before I start with the technical stuff, let me say who I am. Of course, this work that I'm going to present, or this research that I'm going to present, is not done by myself alone. I work with some college research team that we used to call us Indiotech. And well, these are the pictures. I'm the last one if the picture is too old. And where I am in Aguascalientes, which is exactly in the middle of Mexico. Mexico City is, if I don't make mistake, is this part. This is Mexico City. So you have an idea where is Mexico and where is Aguascalientes. Well, now you know where I am. You know that I don't work alone, and you know that this is a team effort. So let me start with the introduction. What is text classification? Well, text classification is the task that tries to classify a set of documents into a number of predefined categories. So the first part is that you already know the categories, and the second part is that you have a set of documents or a set of text that you want to classify. For example, I do apologize because some of my examples are in Spanish, and I will try to do my best that in the last part of the presentation and in the live part of this talk, I'm going to use a data set that it is in English. So please bear with me in the Spanish part. So for example, polarity, which it says that tomorrow I won't be able to go with you guys to the library. And then my question would be, is it positive? Is it negative, that sentence? Is it neutral? Well, you may think that, well, it is negative in the sense that I won't be able to go with you guys to the library. But if I don't like to go to the library, then for me it would be positive. So my point here is that polarity or text, or in this case, which polarity is confused sometimes, or it is similar or equivalent to sentiment analysis, is a subjective task. So it depends of the person that is labeling the text, or the experience that person has. So if I don't like to go to a library, then the being able to go, it's a positive thing, and it is not a negative one. But the guy that wrote this presentation, not myself, like to go to the library, so it is negative that he doesn't go. Well, polarity, which is kind of sentiment analysis, is kind of it tries to classify a text or a document into almost three things, which is positive, negative, or neutral. But there are other tasks that can be set into the umbrella of text classification. This is, for example, emotion. You have a text and you want to know which emotion that text has, or the intensity of the emotion, or whether the text has a violent event or a crime, is expressing a crime. Some of my data set that we are going to use in this presentation is about the latest one, which is the crime. So identify whether a text express that a crime has been committed. So that is also a text classification. And another important part, not as this example or these tags are about the text. So there is another problem that it is also classified as a text classification, but it is not about the text itself, but it is about the person who writes the text, and that it's also that task or that task is known as author profiling or profiling. And for example, in that case, one wants to know whether a particular set of texts are written by a male or a woman or a not binary or any, or what about the age? Is it written by a child, a teen, an adult, or more specifically, a particular range, 22 to 25 or something like that? Or also important is to, for example, to know the variety, the language variety. For example, in Spanish speaker people comes from different countries like Spain or Cuba or Argentina or Colombia or Mexico and so on and so on. English, for example, is speaking in United States, in England, in Australia, and there are other Arabic countries that are Arabic language that are speaking in another countries. And it is interesting to also to classify or to find an automatic way to understand whether a particular text comes from a person that was born in Argentina instead of Mexico, well, just for having some kind of trying to produce some statistics or trying to understand the difference between the variety of different of a dialect in a different country. Well, and these tags are author profiling. So now, so far, I have described what is text classification. Sentiment analysis is also known as polarity. Another part, which is the author profiling, which is not about the text itself, but it is about the person who writes the text. Now, how can we build an algorithm? How can we train an algorithm to predict or to solve this problem, to solve text classifications? Well, there are different approaches, but the approach that I'm going to explain, and I will say that this is the most common approach, is to use machine learning. And well, let me start with that definition of machine learning. Please bear with me if you already know all this. Well, I do apologize. I did this presentation trying to address different backgrounds. So machine learning is a field of artificial intelligence that focuses on the development and implementation of algorithms capable of learning from data without being explicitly programmed. And broadly, there are three types of machine learnings, which are unsupervised learning, supervised learning, and reinforcement learning. And text classification belongs to supervised learning. Well, at least the way that we are going to do belongs to supervised learning. And in order to explain what supervised learning is, well, let me try to just write to plot some points and to assign to each plot a color. What you are seeing here is the famous iris data set. So there are 3 classes, and it's only projected into a 2-dimensional space so we can see, but it's in a 4-dimensional, originally it's in a 4-dimensional space. So each one of the points represent a particular flower, and so you have 3 classes. And the idea of supervised learning is how can I build an algorithm that can split these 3 points by color, so you can so the idea is how can I build an algorithm that can group these ones and can group these. I'm not going to be very good at this, and then can group these ones and then the rest ones. So of course there are 3 classes and it would be more difficult to explain. So I'm going to move on and just try to have only 2 classes to have binary problems, which are easy to implement. So the same idea. So you only have 2 classes. One of the classes are the blue, and the other ones are the red. So how can we build an algorithm that can solve this problem? Well, that's kind of easy. So if you plot a line that divides this space from the positive side of the plane and the negative side of the plane, particularly, that is solved. So just draw a line and that's it. That's the core of machine learning, and that's the whole idea of machine learning. In particular, of course, not all the problems we can see. We, as mentioned previously, we can see this problem because it is projected into a 2-dimensional space, but originally is into a 4-dimensional space. And the problem that we are going to deal with, which is text, is in 1,000, 2,000, 10,000 dimensional space. So clearly we cannot see, but the idea is that we are going to draw a line or a plane or a hyperplane in this space, and then we can split the ones that are positive. So as you can see, this is the P corresponds to the positive side of the hyperplane. In this case, there is a lane, and N corresponds to the negative side of the hyperplane. What it is interesting is that when I'm drawing here a line, that line is just well, it has a nice properties because we can, for example, this is the line that we are seeing. So G represents the decision function, and that are the coefficients. So here you have x1, and here you have x2, and this is the bias there. And interesting is that this line, we can see this line as follows. It lives in the same space that the problems live, that the points live. So you can see this dot. I'm just going to highlight that dot. As you can see, the coefficients of that dot are the first 2 coefficients. And then you will try to understand, well, what is this point? I'm trying to explain this because later we are going to use these facts. And then what is this part? Well, this is just the bias. And let me see if I put what happened if I just change the bias from 0.88 to from minus 0.88 to 0.88. Well, if I change it, this is in the gray one is the original one. If I change it, I'm just moving the plane. Just moving the plane, it is a parallel from the original plane. So now you get an idea of what the bias is doing so you have the geometry of this algorithm. And the second part is, well, what is this point doing? Well, this point is doing the plane, but what happened if we move the point? Well, I just wrote, I estimate another linear algorithm, which is a logistic regression. The first one is support vector matching, and both of them are linear. And you can see in this part, you can see the coefficients of both of them. And interesting is that they live on the same place. So you have here the points, the data set. You have here the point that represent the hyperplane, the gray one, and you have here the point that represent the other plane, the other line, which corresponds to the logistic regression. So what you can see is that this that these parameters, what they are doing is they are rotating the plane, rotating the hyperplane, and this number is just moving the hyperplane from the origin. And well, it's very simple to see what a logistic regression or support vector machine is doing in 2 dimensions, and you can extrapolate that one to 1,000 dimensions without any problems. You just have an hyperplane, and then the coefficients are rotating it, and the other parameter, the bias, is moving the hyperplane. It is a parallel from the hyperplane that is on the origin. Well, now that we have talked about machine learning and how can we solve it, generally I just described a very simple algorithm, which is a linear support vector machine, a linear support vector machine, and a logistic regression. I didn't explain how to solve the problem. I just use a library, or explain that you can use a library, and pretty much you have it. You can solve it. Now let's move on, because let's move on to text classification. So what is the starting point of a supervised learning problem? Well, the starting point of a supervised learning problem is that you have a data set. In this case, sorry for that it is in Spanish. In this case, the data set is text, where each element, we are only seeing the first 8 elements of this training set. Each one has the following structure. So you have a text, and associated to that text, you have the class or the label. Then you have another text, and associated to that text, you have the label. And so you have another text, and associated to that text, you have the label, and blah, blah, blah. This data set particularly is about detecting, already mentioned in a few slides back, is detecting whether a crime has been committed. So 1 means that the text tells us that a crime has been committed, and that is the positive class, which is associated with 1. And 0 means that the text doesn't have a crime. And well, that is all about. For example, this one is that an old person has been detained by some improper conduct, sexual improper conduct. So that means that it is 1 because has been detained, and it is expressing that it is a crime, that a crime has occurred. Well, I don't know. It's very early it's very early for you guys. It's late for me. So don't know if I'm being clear. So what about this quiz? Anyone can tell me if the previous data set, what is the previous data set? If this data set that I briefly explained, is it corresponds to the polarity task, to the motion identification task, to the aggressive detection task, or to profiling, auto profiling? Which one do you think is more appropriate? Okay. Anyone? Okay, I'm assuming that everybody is shy and doesn't want to open the mic and just raise the hand. But please stop me if I don't being clear, or if you want to ask the question. Well, the task is more appropriate to aggressive detection, so it's kind of more related to aggressive because it's about crimes. But of course, it is not about polarity, because polarity is very clear about neutral, positive, negative. It's not about emotions, because emotions, anger, fear, sadness. So it's more about aggressive. And profiling is not about the text itself. It's about the person who writes the text. So it's about age, about language variety. Now that we understand what is this data set. So now comes the problems. The problem is that the independent variable in the data set, well, the independent variable are texts. And we cannot do anything if they are texts, because to solve a supervised learning problem, what we have is numbers. Look, you have X and Y, and both of them are numbers. You have X and Y. Everything is a number in this graph. And this is of course, in a two-dimensional space, this is a supervised learning problem. And the solution is also a number. The black one is also the solution, so it's also a number. And well, that's pretty much the problem. That we have, instead of having as an independent variables, instead of having text here, we want to have here numbers. How many numbers? Well, as much as we can, or the number, it really doesn't matter, but we want numbers there. So how can we solve that problem? Well, what we need to do, and what is normally do, is to represent the text in a suitable format for the classifier. So the suitable format is to have to represent each text as a vector. And the idea, all the algorithms that are old and new come from share the same idea. First one is that each token, we can think of tokens as words, but token is a more general term, in my opinion. Each token is associated to a vector. The vector could be sparse or could be dense, but it's a vector. And the sentence also is a vector. So you have the text, which are associated. You have the tokens, or you have the words that compose the sentences. They compose the sentence, and each token, each word is associated to a vector. And then the whole sentence is also associated to a vector. And if it is a vector, you can feed it to a support vector machine, or a logistic regression, or you can feed it to an artificial neural network, or whatever algorithm you want to do it. You want to use it, and then pretty much is solved. So the problem is hard, and the problem is that we have text as independent variables, and the solution is that, well, we need to change the text to a vector, to a vector representation, or we need to transform our text into a vector. And the idea, the most basic idea, is that each token is associated to a vector, and then we build from that. Now we are going to call that text representation. So the idea is that each token T is associated to a vector that it is in a d-dimensional space. Let B, this B, represent the set of all the possible tokens, or represent the whole the vocabulary, and let D represent the dimension of the vector. Now, if D is less than the cardinality, or than the number of tokens that you have in your vocabulary, then we can find different approaches like LOF, or word2vec, or fast text, and all different deep learning approaches that has followed this path. And these are kind of given that D is less than B, then it cannot span the whole space of the. Well, it needs to be a dense vector in some sense, that if you have zeros in there, then you are more restricted, and you want to have some freedom. And on the other hand, if you have D, which is the dimension, equals to the number of tokens that you have on your vocabulary, then you can think of it as a sparse vector. And the idea of that, that is the idea that we are going to develop here. It's an old idea or a traditional approach that that works good in some problems and it's not so good in another problems. And pretty much if you have a sparse representation, what you have is that if you have the if this is the vector that represents the token I and this is the vector that represents the token J, these are orthogonal, so the dot product is equal to 0. And that is for everything, for all the different words. So it means that the distance between two vectors and two words is the distance is 0. So they are well, not the distance, the similarity between two words are 0. On the other hand, just to put an idea, these approaches, instead of these approaches, law, word2vec, or fast text, instead of assuming that the similarity between any word is 0, what they try to do is to group words that are similar. So you can have the cluster of fruits, or you can have the cluster of cars, and so on. So you try to cluster. So it's not as simple as this one, which just imagine the simplest way to represent a word in a vector. So, and of course, if we follow that idea that you have a sparse vector, then to have a solution to represent that, to have a token, to associate each token with a particular vector, then the algorithm that we can use is very simple. For example, you just sort your vocabulary and you keep it sorted, and then you associate the I token to the I position in the vector, and everything else is 0. And I put here beta because you can either set 1 and you have just one hot vector. One hot vector means that everything is 0 and there is one place where it is a 1, and the position of that 1 is the position in your vocabulary. Or you can have a beta that is greater than 0 and it represents something else. It is a number that tells you something about that particular word, but it doesn't tell anything about the other words in the vocabulary. We are going to develop this. I'm going to explain in more detail this, and I'm going to give all the information to do it. Now, so far I described how to associate a vector, a token with a vector. But what about a sentence? Well, a sentence is just the sum of all the vectors that are in the sum of all the vectors that corresponds to all the tokens that build the sentence. So imagine that you have U, and U contains all the tokens of the sentence, and then X represents the sentence, and it is only the sum of all the vectors involved in the equation, and that pretty much works. That pretty much works. One tip is that sometimes it works better to have unit vector. So you just normalize the vector to have a length 1. And that is not well, that's kind of a trick that works, but should work the other one. But for some algorithm, it is better for particularly for support vector machine is better if you put it into unit vectors. Now, let me describe the process to obtain the tokens, to have the whole idea, the whole process to associate a token to a vector. So you have the text, then you cannot use the text by itself. You first, normally it is a pre-processing step that it is text normalization, and then after text normalization, it comes the tokenizer, which is going to split the sentence into tokens. So what is text normalization? Well, for example, you want to remove the users or the URL, or maybe you are not interested, you want a case sensitive or case insensitive, you want to remove the punctuation symbols or the diacritics or so on. So text normalization reduces the size of your vocabulary. So instead of having Mexico with capital M, you have Mexico with all lower cases, and without diacrit. Mexico has a little diacritic in the E, so maybe you don't want it because normally people misspell it, and well, that's normal. And let me try to describe, for example, the process of remove a diacritic. So if you have Mexico, as you can see here, there is the E as a diacritic. So you just normalize with Unicode, and you know where these diacritics are, and if you find it, you just skip it, and then at the end you have Mexico without that part. And what it does is that if some people write Mexico in the right way or write Mexico in the in the wrong way in Spanish, then all of them goes to the same place, which is Mexico without a diacritic. And of course, there are more things to do with text normalization. For example, you want to do lowercase, the same place, the same example. You have Mexico, and then you move it to just having lowercase. Or if one of the data set that we are working on, that we are going to work it comes from Twitter. Sometimes what you want is to remove the user because you don't want to have to inference anything about the user, in order to be well, not polite, it's not the word, in order to comply with the legislation. So you may want to use text normalization and replace using regular expressions, and replace the way a user is done in a user is done. I don't think that's user. I made a mistake. This is not user, this is URL. Sorry. I make a wrong example. Well, now after you do after you normalize your text, what you want is to transform your text into tokens. So there are common types of tokens. For example, you have words, you have n-grams of words, or you have q-grams of characters. Also, you have skip-grams that I'm not going to talk about, but it's just words where the middle two words that are not together, but that are continuous, and you skip one word. And for example, if the words are very easy to obtain, at least in Python, you just need to use the method split, and then you have words. For example, I like playing football, and here below you have the tokens, which are the words. The n-grams, which are made of words, well, for example, is I like playing football, and you start having the words, and then you just say, okay, how many words I'm going to join? So n-gram is going to be 3. If you have 2, it's called b-grams, 3 grams. So we are going to implement 3 grams. And well, just a little trick about Python, so we can make the code a little bit shorter, and the result is that from I like playing football, the first n-gram is I like playing. The second one, as you can see, just move a little bit, and it is like playing football, and so on. You move a little bit, and then you move one word, and then it's playing football on, and finally the last n-gram is football on Saturday. And what n-grams are doing is that they are kind of capturing the context of the sentence, so in a very naive way, but they are capturing the context of the word and its surroundings. And the q-grams, on the other hand, they are very useful to capture some spelling errors, and the q-grams goes into the character level. So if you want to do q-grams, it's pretty much the same idea, but now you you don't start from words. You start from the sentence from the character. So I just put an example. I like playing, and the qgrams number 4. And as you can see, the first qgram is going to be I like. And you can see there are 4 characters. The space is 1 character. And then you just move 1. And then the space is another character. And that is the second qgram that you find in that sentence, and so on. So far I have explained how the process is to normalize the text, and how to create after you normalize a text, you transform that text into tokens. There are many libraries that implement this idea. Here I'm just going to use one library that we as a research group implemented, which called text model. And the idea is that, well, it has some options that I described, for example, URL or USR, remove the user or delete the user or group the user, do lowercase, and so on. And the most important part is how you are going to use if you are going to use bgrams, skgrams, ngrams, or qgrams, or words. So -1 refers to words. And for example, here we have the library, and then we want to tokenize. And we have I like playing football with myself. This is my Twitter account. And given that I'm removing the user in the output, I shouldn't be seeing my username. So the output after I tokenize is I like playing, as you can see, lowercase, because lowercase is that one. And you can continue with that. -1 is words, -2 is bgrams, so ngrams, where n is 2, and 6 is qgrams of 6. So qgrams of grams of characters with the q equals 6. The other parameters are the same. And I like playing, you can see this is the whole tokenize. And you can see here is I like playing, the word I, the word like. These are the bgrams. As you can see, the bgrams are split with this symbol. And then comes the qgrams, and the qgrams has a prefix that start with q and two points, column, in order to be able to know whether we are talking about a bgram or a qgram, in case you want to understand a little bit what the algorithm is doing. And well, these are the whole tokens of this sentence. As you can see, this sentence is very short, and it has a really long number of tokens. And it's only because I put 6. If I put another number here, you will have more. You can have -3 or 1, 2, 3, or so on. Now we are reaching to the part where we can do some experiments, and of course we are not doing in the slides, but I'm going to try to describe what we are going to do. As mentioned, the starting point of everything that has to do with text classification is that you need a training set. So what we are going to use is a training set that as a research group label. So that's why we can kind of share it, because it's our work, and it is in Spanish, and the idea is to identify whether a sentence describes that a crime has been committed. Well, that is the training set. And now let's start trying to figure out how to associate a sentence to a vector. Well, the first part is that we are going to use a text model that kind of groups everything that we have seen, which is normalized and tokenized, the tokenizing and normalization step. We are going to use words, because words are easy to understand, and lowercase, and well, any other person. So First, let us read or let us load the data set, the whole data set into a variable that it is training set. And just to see the first tokens of this first sentence in the training set, I'm going to tokenize it, and this is the result. The 3 words doesn't have any meaning in the sense they are three words random from the sentence, so I cannot understand what the sentence, what is the meaning of the sentence, because we are only seeing the first 3 words. But the idea is that with this tokenize, well, we can use it to kind of implement the vocabulary that is going to be given by the training set. So the first step in order to associate each token to a vector is to know which are the tokens. So the first step is to build the vocabulary. And to build the vocabulary, you need to tokenize all the sentences that you have in your training set, or all the sentences that you have in a data set that it is not related to the problem that you are solving, or something that you get from internet, or that you have books in a digital form. So an easy way to build a vocabulary is to use the class counter in Python. I just subclass that's well. I use this class counter, and pretty much what you need to do is do a loop for all the texts that are in the training set, tokenize them, and then just keep the unique tokens that you can see. So you have the tokens. I use the counter class to update all the tokens. And at the end, what we are seeing here is the most common tokens in that data set. And the most common tokens in this data set is the, in, and the. So these are the most common tokens in any data set are known as top words. So words that come very frequent in a sentence, but doesn't carry too much knowledge, but helps you to build the sentence. This is of, sorry. So these are articles and deterministic. Well, now, once you have the vocabulary, then you can start associating each token to a vector. And what we are going to see is instead of having just one hot vector, we can use one number that is very common in information retrieval and comes from the 70s, I think. So, which is the inverse document frequency. So we are going to weight each token using the inverse document frequency, which is briefly is how many times you have seen a token in all in your collection in all the documents. So remember that this value comes from information retrieval. So the idea is that if a token is in all the documents, then it's not relevant. And if a token is not in all the documents, only on a few documents, then it is more relevant. Pretty much what you need to do is, well, you need to know how many documents you have. In this case, you have n documents, or in this case, it's like 1,400 something. And then you compute the inverse frequency, and the frequency is the number of times you see the token. For example, you see of 980 times, and the inverse of it. And normally it is used in log. Instead of using the raw numbers, or instead of using just the fraction, it is used in log. It is transformed into log. So you just go for all the tokens that you have seen, for all the elements in your vocabulary. You enumerate them, so you can have an index, which is the part of sorting the vocabulary as the first step in order to build this, to associate a token into a vector, is to sort the vocabulary. Normally you can sort it using, well, not sorting, but you associated it, a number with it. So you have the identifier, and you just keep a mapping between the word and the ID, and also a mapping between the word and beta, which is the number that corresponds to inverse document frequency. And we can use it, for example, to calculate or to compute the term frequency and term frequency inverse document frequency for any text. So here, what I'm doing is just getting the fourth element of the training set. This is the text, and then tokenize the text and use the tokens that I computed, count the number of unique tokens that I have, also count the number of times that unique tokens appear in the sentence, and just iterate for it. If the token here is a very important part. This part is very important, and it happens frequently in any problem in natural language processing, which is what happens if you have a new word, a word that has not been seen before. Well, if you have a new word that this code is telling me, if the token is not in token to ID, so I haven't seen it, well, I just continue. So pretty much is if you have a new word or a word that it is misspelled and haven't seen it, well, you just drop it, and you kind of miss the knowledge of that word, but you cannot do anything. So you just drop the word. And well, once you if the token is known, then you have the value of beta, and you also have the number of times you have seen that word, and well, just the number, the term frequency inverse document frequency. Well, it's just the product between term frequency and the inverse document frequency. And here we are seeing the first four numbers of this representation of the text that we are not seeing, but of the text that it is in the fourth position on the training set. And you may wonder, where is the tokens here? Well, 54 is the 54 token that you have in your vocabulary. So if you want to know which one is, you go to this place that you have stored, and then you can retrieve, you can know what 54 is. So you can know the token. And you also may wonder why you have only 4 elements. Well, I only have 4 elements because I only display 4 elements. But my point, what I was trying to tell you, is that you have a big vocabulary. In normal cases, you have 50,000, a vocabulary of 50,000. So a sentence that only have like 100 tokens, it only requires 100 components of the vector, and the rest of the components are zeros. So that's why here you have like a sparse representation of a vector. You have the index and the value, and the index that doesn't appear in the representation, it means that they are zeros. I hope it's clear. Well, clearly we are not going to implement all of this. Well, but this is the whole idea. So what we are going to use is it's a library, and pretty much exactly the same, which is just going to feed it. Feed it means that, well, this is a text model that we have used before. So we are going to feed it with the training set, and feed it means this part. A little bit more code, but pretty much is this part. And then once we feed it, means that once we have the inverse document frequency for each of the tokens, we can transform or represent a text into this vector space. So we only call it, And we can see here the text representation of this, of the text that it is here. The first thing that you notice is that, okay, these are small numbers and these are big numbers. These are also, the index is high, and well, it is because in this case, don't remember exactly what were the parameters. The parameters are only words. Well, it depends on how the different words. So at least we know that there are more than, at least there are 6,598 different words in the training set that we train the model. And these are small numbers because I use the trick that they are normalized. So all the vectors are unilateral, have a length 1. And in this case, we didn't normalize it. So that's why the numbers are higher in this case than in the other case. Well, it comes another question to see if everybody is awake. From this code, which one do you consider it produces a larger vocabulary? The difference between these two codes, it's only here. So the difference is, oh, sorry. The difference is A uses this one and B uses this one. So which one do you think produces a larger vocabulary, A or B? Anybody? It's just A or B.
A.
Well, thank you for answering. And I'm going to thank you very much for answering for, and I will try to explain a little bit because it's interesting. So -1 is in both, so they will produce the same number of or words, and so the difference is between 3 and 6. Now, for simplicity, let me assume that our vocabulary only has 2 values, so you only have zeros or 1. For example, in Spanish, we have like 27 letters or 28, I don't remember. And in English, there is like at least 2 less or 3 less. Well, anyway, if you only have 2, then it means that a character of length 2, so you have either 0, 0, you have either 0, 1, and so on. You have 1, 0. And if you have 3, you can just keep it like that. And you can, for example, put 0, 0, and then you say, and then you start changing. So how many possibilities if you have 3? I don't remember if it's 3, but how many possibilities there are if you have 3, a length of 3 and only 2 characters? And what happens if you have a length of 6? So you have 1, 2, 3, 4, 5, 6. How many possibilities do you have here, and how many possibilities you have here? So kind of these are the possibilities that you have in here in this tree, and here is the possibilities that you have here in 6. So as you can see, you have more possibilities here. So the vocabulary is going to be greater in B than in A, because you have more options here. And the Q-grams are fixed. So the length is like this one. And the different letters are fixed. So this value 0, 0 or 1, or 1, 2, 3, or whatever, is fixed for both of them. So it only depends on the length of the character. So if you have if you allow a longer sequence, then you have more possibilities. But many thanks. I hope I explained. I make myself clear why you have a bigger vocabulary here in D. And it was not an easy question. Just to let you know, I did that in a test while I was doing while I was giving lectures in Colgate, and it was also very hard for the students, even though that they have spent the whole semester studying this. So now we are almost done at the part. So what we have seen, you have a text, you have a training set. That training set, you already know how to transform each text in the training set into a vector. So pretty much we have seen that. So the rest, now that we have a vector, well, the rest is just use a classifier to support the problem. So the procedure to summarize this, the procedure is to, okay, I'm going to use the training set. I have a text model that I already use, and I'm going to transform all the text that I have in the training set. I'm going to transform it. That means I'm going to have it on a vector space that the variable I'm going to call it X. And then once I have X, well, what I can do is, well, what about the classes? So I just take out the classes and I call them labels. And pretty much I train a 4-vector machine using X and the labels. And if I train it, well, I have the model here, and I can use the model to predict. So, for example, I'm going to predict good morning, and even though that the training set is about crime, and 1 means that a crime has been committed, well, not committed in the sense that the text indicates that a crime has been committed, and if I say good morning, the model says 0, meaning that good morning is not a crime, which is correct. And of course, it is a very simple example, but the process, the whole process of text classification is summarized in these 3 steps. Prediction, as you can see, it starts with the text. Then the second part, transform the text into a vector. The vector is stored into a matrix, because if you want to predict, normally you want to predict more than one text. You want to predict more a set of text, and then you use the method predict of the linear support vector machine to predict the label. So far, so good.
Yep.
Perfect. Well, once you have the problem, once I describe the whole idea, and once you implemented the whole idea of this, we want to measure. Normally, we want to measure the performance of your algorithm, and in this case, I made a little bit of code to measure the performance of the algorithm, which is using a fault cross validation. The idea is to split the training set into 5 faults. And well, so you have a loop, and for each part, you have a training set and a validation set. So you have the training set, which is this one. This entrain, you have the training set of each fault. And then for each one, you have the validation set. You train the text model on the training set, as you can see here, the train, and you estimate the parameters of the support vector machine. As you can see here is the transform of the train, the labels of the train, and finally you make the prediction. And you make the prediction. You transform the validation set. You make the prediction of the validation set. Here are the predictions. And then you measure some performance of that. In this case, what I'm measuring is the macro recall score, which is these are the true values. These are the predictions. And this parameter is only to tell that we are computing the macro score. We store the performance for each fold, and we measure the average of that performance. And the performance of the algorithm is roughly 82%. So although macro recall is not measuring the accuracy, what it is measuring is similar to the accuracy, in the sense that if the data set is balanced, then macro recall and accuracy is going to be roughly the same. So is it good? Is it bad? It depends on the application. If, in my opinion, it is not that bad. It's good for the type of application which it requires to identify whether a crime has been committed. Well, now before I reach to the conclusions, I want to change to COLAB. Well, everybody can click on this one, and COLAB. Well, what I'm going to try to replicate what we have done, of course, not in all the details. I'm just using the libraries, but what we are going to do is the whole new example. This notebook is going to use the data set of crimes, but in this session particularly, what I'm going to use is another data set that unfortunately I cannot share with you because it's not my data set, but we are going to use the data set of these guys, which is a competition, well, which is the competition is called HOPE, and it's the HOPE speech. The idea is to identify whether a text kind of have hope in it or doesn't present hope. Instead of detecting an aggressive text, what you want to detect is whether the text provides some hope. So it's kind of the positive aspect of text classification. And we are using that because there are two versions. One is in Spanish and one is in English, and we are going to use the English one. Please bear with me because I decided these 2 minutes before we start, and because I had the crimes, and then I decided that no, crimes was not good enough because I won't be able to explain it. I think already installed some of the libraries. Let me see. Here are just the imports. Let me see if it runs. If it doesn't break, nah, it runs. So we are going to see some word clouds and to see some emojis. Sometimes the word cloud by the font by default is not good enough, so you can use this font instead. And even it is zipped with password, but you can see the password here, so you can just copy and paste it. And now comes dataset, and the dataset, bear with me, we are going to use, instead of the crimes, we are going to use, instead of crimes, we are going to use this one, which is hope in English. And let me see. Doesn't complete. Train. I want to show you some of the elements of the training set. So these are some of the elements of the training set. All of them are not hope. Let's see if I found that one of that it is hope. All of them are no hope. As you can see, here is the class, and the class is no hope. Let me see if the last ones are hope. No. Well, at least you can get the idea of what we are going to see. Now, The first part that we want to do well is to create a model, a procedure that is going to transform the tokens. Is going to transform the text into a vector space, into vectors. In the presentation, in the slides, I described the procedure to tokenize. So let's just tokenize the first element of the training set. Lowercase, you can see there are lowercase, and maybe there are not symbols, and so on, a few other things. And next, what we are going is just get our hands on text classification. Just going to create the text model. We're going to estimate the parameters. We're going to estimate the parameters of the inverse document frequency. And what we are going to do is we are going to transform the training set as we did into the vector space. We're going to take out the labels, and we are going to train a support vector machine. I hope it runs and hope it doesn't take too much. And just wait a little bit. While we're waiting, if you want to ask any question, didn't take too long. Let's see what 33 is. Okay. Well, the class of this one is no hope. So we're going to predict this one. So we're going to predict 43. We're going to transform it, and we're going to predict it and see what happens. And as you can see, the class is correct. And anybody can, most of the times, if you predict the training set, I would say almost 90%, 99% certain, you are going to get the correct class in this kind of experiments. Any idea why? In the training set, not in the test set. Any idea? Well, it is because.
Can you please repeat?
Pardon?
Can you please repeat?
Can I repeat the question? Because why do you think in the training set you are going to get a perfect score? Let me try to do it here in code. So if you have the training set,
sometimes due to overfitting.
and not the question I was not the answer I was looking for, but many thanks. And it is normally it is because it is in a very in this case, given that we are working on text, is because it is in a very high dimensional space. And so you have many degrees of freedom. And so having many degrees of freedom and having a kind of a small data set of 2000 or 1000 or whatever, then what it implies is that you have more freedoms. So you are going to learn everything. That's why measuring in the training set in this kind of examples is not, well, it's misleading. And I just tried to see if I can compute accuracy in the code. So you can see that training set is, if I make a mistake, then my whole idea is going to break. Nah, I make a mistake, don't know where. as you can see, 90%. This is the accuracy of the training set. And now let's measure the performance. So the same thing, we have a training set, we have a test set, which is called develop. And as you can see, here is the develop. Here's the develop, and here is the train. And well, just need to do the same steps that we did before, which is transform the text into the vector space, which is in this line, having the labels for the classes, train a support vector machine, already done, and just predict. These are the prediction, these are the true labels, and we can compute the score. And the score is this one, which is very good for one class and very bad for the other one. And right now, I don't know which one is which. So what we can use is try to figure out which one is which one. And I make a mistake because this is not code. So let me see. So the first one is hopes. So it's this one, and the second one is this one, 97. So this one is very low. So meaning that the problem is a little bit hard for this example. So give me idea of, well, we are going to find very easy in which example we are making a mistake. So in this case, we are assuming that this sentence is NH, no hope, and of course the sentence is H1. Any idea how we can improve this performance?
Sir, by removing the impurities in data set.
Pardon? Increasing the data set.
Sir, I want to ask a question about this.
Yes.
Sir, see, before you perform the analysis, we didn't actually check if the data was well distributed. Imagine we have 90% cases of having a negative sentiment, okay, and 10% cases of having a positive sentiment. Then what happens actually? Won't it happen that making a negative sentiment instead of the positive one will be better in the general case?
Can you rephrase it?
I was just telling that the data is not well distributed.
It is not well distributed. I mean, I don't know, but we can see. So you already see that it is not well distributed, but it is a good idea. Yeah, it is too biased to this class. So one way to change that.
So see what happened. I was just saying that because the negative sentiment is so much that for the machine, what happened is it understood that having a negative sentiment as a general answer would give it a higher probability.
Yes, you're completely right. Don't know if this thing. Let me autocomplete. What good one? Good one. Is there a way to change that?
I think we have to then augment data to actually have a relative scale, or we have to downsize it.
I'm getting nervous. Yes, I get your point. Yes, it is a good idea. I was trying just to figure out if we can find another one that we can try right now. But this, I cannot read this documentation. It's too, it's bad, and my. Two minutes, and if I don't improve it, then we move on. But it is a good idea, what you just tell us. So what we're going to do is we're going to tell the classifier that optimize somehow the classes. I hope I didn't make any mistake. I make a mistake. And if everything goes like planned, it should improve a little bit. So 36 should be a little bit higher. Yeah, just by changing a little bit of the parameter of the classifier, which address the problem that the colleague mentioned, which is that there is a really unbalanced data set. Another way that the question that I was asking is, or my idea, of course, this is my idea was to increment, for example, just write a qgram, something like qgram 3, qgram 4, in that will increase the vocabulary. And if I'm lucky, because you need to test it, and if I'm lucky, it will improve a little bit. Yeah, did it improve? I don't remember, but I think it improved a little bit. I think it was 66, and now it's 69. Well, let's move on and try to make an analysis.
Was it allowing the model to
The beauty about support vector machines or linear regression is that you can, for instance, understand what is happening. And let's just try to, here we have a sentence that it is misclassified. So we can have the weights of we can obtain the weights of the vector. And then, well, we can, here we have the vector that represents that text. We can see the coefficients of the support vector machine, and then we can have the information about how it was created. And given that it is that I use qgrams now, it's a long token list. So you have all the words and you will have all the tokens. So negative means that it goes to HS, and positive, it means that it goes to NHS. That's the way it is. That's the way the labels are sorted. So these are too much. So what we can see, what we can do is, for example, just sum the positives ones and then the negatives ones. I did too. Sorry. Some the positives one and some the negatives one. So this is the negatives, this is the positives, and this is the bias. And if we sum everything, we can see the decision function, and the decision function is to say that it is NHS NHS, which is incorrect because it was HSS, that sentence. No, the other way around, say wrongly. But it's too slow, my computer. Well, but this number, as you can see, this number 0.04, it means that it is close to the decision function. So if it is 0, it doesn't have any opinion about whether it's positive or negative. So if it is close to 0, so it means that it is unknown about it. Although we can see that the number, for example, this is the negative, is way higher than this one. But if we have a text without any text, so our bias is completely biased to the positive side, to the positive side, which in this case the positive means the class NHS. This experiment or this procedure, this methodology can be done in any problem, and gives you an idea how the algorithm is solving it. Also gives you an idea how the relationship between the different words in the sentence are not attached. But for some problems, that's not a problem really. Another way to look into this, into the details of the algorithms, is to have a word cloud. And given that we have for each token, we have the coefficient, then what we can compute is normalize is whether test if the coefficient estimated by the support vector machine is positive, and if it is statistically significant in the positive side, or it is statistically significant in the negative side, and then just keep those coefficients, which corresponds to those tokens that are either positive or negative, and having sorted by this sorted by the confidence that you have it on the positive or negative side. And just wait a little bit and we will be able to see it. And given that this is the first time I see in this problem, I don't know if we are going to be waiting a long time. Sorry for that. Any question while we are waiting? We are reaching to the end part of the conversation, so any question is welcome. Please have questions. While we wait, let's move to my final part. Because, okay, it finished. Sorry. First time that I run this in the experiment.
Hello. Sir, I have a question.
Yes.
So, while we are doing this, when we come through some top words, like some irrelevant words, which cannot give us any information. So, how can we remove them?
How can you remove? What? Sorry. Sometimes my couldn't follow the whole question.
So, the irrelevant words which do not provide us any information, like the statement is about positive, negative, or neutral. They do not provide such information. So how we remove such words?
Oh, how the well, in this approach, it's going to be removed automatically, in the sense that either if they are not related to neither positive nor negative, should be equally distributed. If they are not equally distributed, then what will happen is that that word particular is going to be wrongly associated to one of the classes. For example, let me try to find an example here in the word cloud which illustrate what you are saying. I don't know if you can see my mouse moving. You see that there is a 95%. And given that it is 95%, given that 95% is in the word cloud that represent the most discriminative tokens, well, it means that this is wrong, because 95 doesn't have to be neither, is not associated to neither NHS or to HS, what I can see. So you are going to have you are not going to remove it. You just need to have more examples, and maybe with more examples you are going to remove it, or you are going to have it in the wrong. I mean, you are going to kind noise in your model. One way to approach this, I'm assuming, for example, this token, which is 95%, appears a few times only in one of the classes. Let me see if we can see in which class appears. So what I'm not explaining this. This is the word cloud. Given that you have the coefficient estimated by the support vector machine associated to each token. What we are seeing in this word cloud is the tokens that has the highest coefficient, either in the positive side or in the negative side, given that we are only having two classes. So these are the most discriminative tokens, having 95, and then the same idea, we can use it, the same idea that is used here, you can do it, but only asking for those tokens that are useful for the negative side, or those tokens that are useful to discriminate the positive side. So what I'm trying to figure out is if we can see here the 95. Well, no, it doesn't show up at the first, so I have no idea whether it is 90. It is in the positive or in this or in the negative model. But answering the question is that if there is a token, a word that it is not related to the problem, either you increase the training set or you are going to keep it with that problem. I mean, you are going to set kind of a noise in the model. What you expected is that you have enough information so you can have like the same distribution on both of the classes, or on K of the classes. Also, these kind of word clouds allow you to not kind of tune the classifier, but to understand if the data set that you have, is well collected. If here we can see, if here we see something that it is not related to our problem, in the sense that kind of shows something weird, then we can decide, okay, maybe I collected my data set I am biased in the collection of my data set.
Sir, I do have a last question if you're free about it.
Pardon? Can you repeat that?
Yes, sir. I do have a question. Am I not audible?
I heard that you have a question, and that's the last part that I heard.
Yeah, I thought I wasn't audible at all. Sorry. See, the thing is, I was trying to build a recommendation system. Okay. For a product. What happens is, for example, let's say it's music or any other platform. Sometimes people use, for example, sarcasm. Okay. So at that time, what they mean is completely different from what they say.
Yes, the problem of sarcasm is very complicated. I mean, and there are some, as you can see here, well, the data set that we are using is a data set that comes from a competition. So there has been a lot of competitions trying to infer sarcasm from a text. I think in my personal opinion, the approach that I describe here is a traditional one that works very good for author profiling, but doesn't work so well for the other tasks that are not author profiling, such as sarcasm identification, or even this one is not very good for this one. So approaches more like deep learning approaches, more semantic approaches are more are better. And if you are dealing with a lot of sarcasm, then maybe trying to identify the sarcasm as a different task could help. But please have in mind that the sarcasm identification is a very tough task, which even for a human, it's very difficult. Trying to implement it in a computer is a little bit more. Don't know if I answer. Well, let me just talk about the conclusions. What I describe here is a supervised learning approach to tackle text classifications. I took a little bit of time trying to describe machine learning and supervised learning with a very simple example, and tried to describe the geometry of a linear classifier. It's very interesting because you can once you get the idea of how a linear classifier works on a low dimension, then you can extrapolate to a higher dimension. And the key point is to represent a text as a vector. Either you represent it as a sparse vector, which is the procedure that I have described in this talk, or you represent it in a dense vector, which is normally what it has been done in neural networks, in deep neural networks lately. One key part, once you finish the whole algorithm to solve the text classification problem, well, one important part is to measure the performance. So even though that I briefly described how to measure the performance, or I only produce a slide about it, it's very important. My webpage is here. I share with you guys the presentation, and I share in the presentation, and you can see in the footnote is the Colab if you want to try it. And please write me an email if you have any question or you want to do a follow-up. I'm happy to help.
Well, actually, I do have a question.
Go ahead.
Earlier, you talked about the noisy data. So, how we can resolve the problem of noisy data in the sentiment analysis, like the best approach to solve it?
Can you repeat about the data?
So, we talked about the noisy data in the sentiment analysis. You mentioned that it causes a problem. So, what is the solution? How can we resolve the issue of noisy data in the sentiment analysis?
Having more data, or going through, or going to a dense representation. A dense representation of vectors can have more information stored in it, so you can solve that part. Although if there is a lot of noise, then nothing can be done. But normally there is not a lot of noise. So more data and if more data doesn't help, going through deep learning approaches might help. But the key point is not just to change the classifier. The key point is to use pre-trained models, to use models that have been pre-trained in an enormous corpus, in billions, in millions of text, so that you have a more robust representation. What I have shown here is you only have a training set, and then based on that training set, you build a classifier. Normally, what one does is you not train the, for example, the inverse document frequency values are not estimated in a small training set. They are estimated on millions of them. Well, if you estimate it in 5 million texts, then the inverse document frequency of each term is going to be robust. And then, given that it is more robust, your classifier is going to be more robust. And then the tokens that could be kind of in two of the classes or that involve that produces some kind of noise, then they are not going to be so important anymore.
Hello.
Hello, sir.
Hello.
My God.
Go ahead.
Sir, what would be the current research trends in text classification?
Most of the trends of text classifications are deep learning approaches, in particular those that has to be in text. That has to be good sentiment analysis, emotion recognition, and sarcasm. The trends is to use to start with a pre-trained model and then build on that pre-trained model. On the other hand, the approaches that are commonly used on author profiling, which is gender identification, language variation, or any other kind of thing that has to be with profiling, it's easier to get good performance with the things that I talk about it, with traditional methods, which is called bag of words.
Hello, sir. Sir, can AI help in improving the sentiment analysis?
Could you elaborate a little bit more?
Actually, can AI, artificial intelligence, help in improving the sentiment analysis on large data set?
I think the large language models, which are kind of the large language model, contains a lot of information about what we do online, and contains a lot of information about contains a lot of knowledge. So they are improving somehow the algorithms that tackle the problem of sentiment analysis, which is identify the polarity of a particular text. But for some problem, or for some instances, I mean, there are certain problems, certain sentences that are hard for humans, and for those are still hard for models that are built upon large language models. So on one hand, they help, but on the other hand, there are some kind of problems where perhaps the problem is well defined, where the large language model is not needed, and a traditional approach can handle it. And on the other hand, in a mobile phone or in a place where you have small resources, then a traditional approach is more efficient than a large language model, which is kind of the trend. So it is a mixture of, yes, they are helping because the large language model contains more information, but on the other hand, sometimes it's not easier to extrapolate that more information into a good performance. So yeah, it helps, but sometimes it doesn't, and it depends on exactly on the problem. If it is well defined, let me try to make an example. If you are doing sentiment analysis for a political, for politics, so you try to do sentiment analysis for a person that is doing politics, and then you move to do sentiment analysis for a company, for a brand. These are two domains, and even though you are good in one, when you want to move your algorithm that has been learned in this domain and move to another one, it's not going to be working. And perhaps on those cases, the large language models are going to be better, because they are going to kind of extrapolate that. They are not going to be the best, but maybe they don't suffer too much. So I think.
Thank you, sir.
Hello, sir. Sir, what are the best approaches for text classification?
What are the best algorithms? Could you repeat, please?
Sir, what are the best traditional ways for text classification?
I got lost in traditional.
Speak clearly, beta.
I'm really sorry. So I'm
Sir,
really,
what
really
are the
sorry.
best
Sakshi Mundra,
ways
speak
for
properly.
text classification?
Either you can type your question. Either you can type your question.
Yes, that helps. Sorry for that. Sorry. I do apologize.
No, sir. It might be some network issue from her side. It might be possible. Sakshi, you can type a question, please.
I don't think.
So, what are the best traditional ways of text classification?
The traditional task of text classifications. I think the most familiar one is sentiment analysis. The most popular one is sentiment analysis, but there also another brand which is, I think people is moving to something more complicated like emotions or aggressiveness detection or something more, trying to understand what's happening on social media. So, for instance, aggressive to a particular group, aggressions to a particular group, to identify whether your comments here is aggressive, but not to everybody, but just to a particular group, from gay, lesbian, or something like that. That's also a very big trend right now. Identify migrants that people try to express correctly towards migrants. It's also very important topic that so people is moving just from polarity or sentiment analysis to other tasks that can kind of be implemented in a social media so that everybody can feel more secure when speaking or when expressing their own opinion. So, which is very hard because if you have an algorithm that is going to kind of restrict what you are saying, then it goes both ways. And somehow people feel more free to speak, but in other part, then you are restricted to only say what maybe you don't think about, what you don't think. So kind of that's the trend in text classification.
Sir, I have one question. Unlike in sentiment analysis, we use text classification. Can we use text classification in building a project on automatic translation to something?
Could you repeat the last part?
Sir, can we use a text classification approach in building a project on automatic translation?
Most of the of NLP problems can be posed as a text classification. The trick is that, for example, in translation, then the problem is that you in sentiment analysis or in polarity or in the things that we saw, you have a text and then you only have one class. So you have a sequence, and then you have a class. But for example, in language translation, you have a sequence, and then the prediction that you want is another sequence, maybe of different length. Although they can be posed as a text classification, one must deal with the fact that you have on both hands sequences. So it is posed as a text classification, but a text classification that can deals with a sequence. And what we have seen, no, what we have seen cannot be posed as a sequence immediately. Maybe no, it might be easier to follow another approach, and might be easier to follow a deep learning approach in that context, because in a deep learning it is easier to set the problem sequence to sequence and with different length. And here what you have is a sequence, which is the text, and then even the sequence is transformed into a fixed length sequence, so into a fixed length vector, and then you have a class, which is just an output. So to answer correctly, yes, most of the problems in NLP, in natural language processing, are in fact text classification problems, but what we have seen here is a text classification with the restriction that you have a sequence and a class, and other problems require to have sequence to sequence, although the sequence to sequence is text classification.
Thank you, sir.
For example, question, but many thanks for your question, because then I just remember, for example, question answering, which is you have a question and you want to know whether the answer to that question is true or false, is posed as a text classification, so in the same way that we are doing, because you have a question, which is a sentence, and then you have the answer. So you have two pairs, you have a pair of sentences, and then the answer is only saying true or false. So true, the question, the answer is the answer to the question that you are given, or false, they are not.
Thank you, sir, for such an enlightening session, and everyone for their active participation. Before moving to vote of thanks, I would like to request everyone to turn on their cameras, as we would love to capture these moments of this session. So kindly turn on your cameras for some moments.
I hope you have enjoyed the talk, and I really appreciate all the questions, and I really appreciate all your patience towards me, because of course it is not easy to be speaking English, whether both of
So it was absolutely a great session. And for the vote of thanks, I would like to invite Bhutesh Kavar ma'am.
Thank you, dear. Very good morning, sir. I am very much obliged to give vote of thanks on behalf of CIS Freedom Branch Chapter of IEEE. First of all, I would like to express my sincere gratitude on behalf of PIET to Mr. Graff for this beautiful, insightful session. Mr. Graff's expertise and passion have truly enriched the understanding of text classification and sentiment analysis, paving the way for new insights and perspectives. So thank you so much. It was very nice session. Every student has involved deeply into that, and that is very much appreciated. Thank you so much. Secondly, I would like to thank our director, Principal IEEE, Dr. Dinesh Goyal sir, for supporting on all the aspects to conduct this session. I would like to thank and appreciate the teamwork of CIS team of our college and the anchor of the day. Thank you so much, the team and the anchor. I also wanted to extend my appreciation to all the participants because without them, the session will not be a successful one. For the active engagement, thought-provoking questions, and enriching discussions. As we conclude the session, let us carry forward the knowledge and inspiration gained today into our respective areas. We will continue to explore, learn, and innovate in fascinating journey of text analysis. Thank you, residents, sir, for your enlightened presence, and thank you all for your enthusiastic participation. We look forward to welcoming you to future sessions and have a great day ahead. Thank you, sir. We definitely want you to be in more sessions with our chapter. Thank you so much.
Thank you very much.
Okay. Bye-bye, sir.
Thank you. Bye-bye.
Students?